Let us start lecture 37, and the course is phase diagrams in single component and binary systems. And today's topic we will discuss on condensed ideal solution, and we will be taking solid and liquid solutions. And also we will try to look at the common tangent rule, and that would give us an idea of equilibrium between two phases existing in a closed system and where temperature and pressure both are constant. So, that will be today's topic. We have gone through the concept of tangent, and also we have also found out how to decide the intercept of that tangent over any point of G2 line, which is basically the solution free energy, and that tangent wherever it cuts when the Xa as well as Xp are 1, that means pure condition, that would be considered as the molar partial Gibbs free energy of component A and B in the solution considering binary ideal solution. So, let us just note down all those conditions and formulas, and then we will see what it means for common tangent rule. Now, we see that G2 equal to G1 plus delta G mix, and where we have taken binary ideal solution that can be solid as well as liquid solution, and we have A and B, these are the two metals. We are taking alloy formation, solid alloy as well as liquid alloy. A and B, Xa and Xp are basically the number of moles in 1 mole solution. So, that becomes that actually then these two quantity becomes the mole fractions. So, these are the mole fraction of A and B when we are making a solution of 1 mole. So, that means this Xa and Xp also become number of moles of A and B, and this goes to 1 mole. So, that means Xa and Xp are basically mole fractions also, because Xa, if it is a number of mole divided by 1, which is the total number of moles. So, that means it becomes mole fractions. Temperature we are actually going to see at a fixed temperature. So, this is fixed, and pressure we are taking 1 atmosphere. So, that is the condition we have imposed, because all the natural processes happening is basically most of the natural processes, those are basically happening at 1 atmosphere. So, that is what we are taking pressure to be 1 atmosphere. That helps us to visualize the standard condition. Now, there are other things which are applicable. For example, Raoultian solution rule is valid. So, that means they have similar atomic size and they are soluble over the entire composition range, and also their bond energies, that means AA, BB as well as AB bonds are same. Now, we can also put one more conditions. Let us say we take the structure. So, whether it is FCC or BCC, that crystal structures, let us take the crystal structure is also same. For both the metals. Okay. So, these are the conditions we have imposed, and G2 is basically for the solution, and G1 is basically unmixed. This is for solution, this is for unmixed condition, and this is basically the mixing quantity. Now, G1 can be written as XA GA naught plus XB GB naught, where GA and GB naught are these are basically pure metal gives free energy, molar gives free energy. Fine. Okay. So, these are the conditions we have said, and delta G mix nothing but RT XA ln XA plus XB ln XB. Okay. And G2 can be also written as XA GA bar plus XB GB bar, where GA bar equal to GA naught plus RT ln XA and GB bar, which are basically partial quantities, GB naught plus RT ln XB. So, these are the formulas. Now, we have actually seen how G2 comes up on a G versus X plot, that is a free energy composition plot. So, this is G versus XB plot. So, I am taking XB as the, with reference to B, I am trying to see how the G varies. So, there we have seen this is delta G mix, and let us say if I, this is 0 values, this is G XB this way, fine. And now we have, these are the XB, this is GB naught, this is GA naught pure condition, and here XA equal to 1 and XB equal to 1. Okay. So, then I can find out G1 here, this is G1, and then correspondingly I add up all the del G mix values at different compositions, then I will get a plot like this. Okay. So, this is G2 okay, for the solution. So, now we will just only plot for G2. So, if I try to plot G2, you just go back to the previous lecture how we have found out G2, you can do that. And remember, whenever we are trying to find out G2 for a particular phase, let us say we are talking about solid solution, then G1 should also be for the solid and all the composition should also be for the solid. Okay. You cannot mix while considering solid solution, the composition cannot be of liquid solution, fine. So, that you have to make sure. Now, if I try to draw only the G2, let us say I have drawn a G2 line, this is G2. This is GB naught, this is GA naught, this is XB, XA equal to 1, XB equal to 1. So, that means this is my G2 for the solution. Now, let us say I have to draw one, let me just extend this. Okay. So, let us say I want to draw not common tangent here, it is a tangent here. Okay. So, let me draw a tangent. Okay. A tangent is drawn at this point, this is the composition, let us say this composition is C and let us say this is for solid, okay, or let us say some other phase, some arbitrary phase which is alpha, okay, homogeneous. So, let us say this is alpha composition of that point where the tangent has been drawn over G2 curve. Now, I can actually find out G2 alpha at C alpha can be written as, and C alpha with respect to B, that means XA GA bar plus XB GB bar, and here XB at C point. So, let us say this is C point, let us say this is Q point. So, at Q, which is C alpha. So, that means, and we know that XA plus XB equal to 1. So, hence I can write this G2 alpha C alpha equal to 1 minus C alpha with respect to B. So, 1 minus C alpha, because XA becomes 1 minus C alpha GA bar plus XB GB bar. And what are those GA bar and GB bar? This is my GA bar and this is GB bar. Last class we have seen that the tangent over any point of G2 cutting, intersecting at the free energy axis at XA equal to 1 and XB equal to 1. So, those are GA bar and GB bar respectively. Those are the partial quantities or chemical potential of A and B in the solution, which is G2. Now, let us come to this particular two quantities. Chemical potential is nothing but escaping tendency of, or particle, let us say, particle from one phase to another. Fine. So, this is escaping tendency. Now, and of course, when we fix an T and P constant. Now, if we say that, for example, escaping tendency any of those components GA bar same over a large concentration of a phase. Okay. So, I can say that with respect to A, the particular all those composition, all those phase concentrations are in equilibrium, because we see that the escaping tendency of A from that phase at all concentrations are equal. So, that means with respect to A, all the concentration are in equilibrium, or we can say compositional equilibrium. Similar applies to B, GB bar, same over large concentrations of a particular phase, let us say here alpha phase and here also this is alpha phase. Okay. So, all the concentration I can say that alpha phase with respect to B also the system will be in equilibrium with respect to B also. And in order to reflect the phase in the chemical potential or the molar partial quantity, chemical potential is nothing but the gives partial molar gives free energy of any component in a solution. So, I will just put in a superscript, this is alpha, this is alpha, okay, since we are considering alpha phase. Now, I can see that this tangent over this tangent any point if I consider, let us say this point, this point, this point, this point, any point I consider, I see that at all the points the partial quantities of the chemical potential GA bar and GB bar all are same, all the concentration if you keep side by side they will be all under equilibrium at a constant temperature and pressure, fine. So, that suggests that over that entire tangent line, I can actually switch from one concentration to another concentration under equilibrium when the chemical potential of both the components A and B are same. Okay? And that can only be possible if we follow up that addition of another component into another composition, into a particular composition reversibly. Okay? So, for example, let us say I want to switch from this point to this point. I see that the chemical potentials are not changing, but I still remain this, both the composition would be under equilibrium, because I have to add up B to C alpha in order to get the composition C. So, this is the composition, let us say C composition. Okay. This is the C composition. So, and these addition should be done reversibly. So, then composition C alpha and composition C, these two compositions will be in equilibrium. Okay. So, now I can actually get the free energy values at C just by changing the concentration without changing the chemical potentials of A and B in the alpha phase. So, that is basically another alpha phase line. So, in order to reflect this particular thing, I can put it here as alpha alpha. Now, I need to change G2 alpha, which is the solution of alpha. I am changing to C, concentration C. Initially it was at C alpha. I will write it as 1 minus C Ga bar alpha plus, change it here, it should be C alpha. It will become C Ga Gb alpha. Okay. So, this particular thing happens when composition is changed from C alpha to C by adding B reversibly. Since reversible process always will be under equilibrium, and that should be added infinitesimally, so that the system would not be allowed to move away from the equilibrium line. So, this is my new free energy, which is at this point. This would be my G2 at C, and here it will be G2 at C alpha. Okay. So, this particular, so that means over that entire tangent line every point will be under equilibrium, and I can easily get the free energy values by shifting the composition like this. So, this same concept can be used to find out the equilibrium between two phases. So, let us look at that equilibrium between two phases, how it appears. Now, let us say I have a system where I have two phases, alpha and beta. So, let me just draw that. Okay. So, this is G x b, x b equal to 1, x a equal to 1. So, now if I draw one, this is let us say alpha phase, this is alpha, and let us say one more phase which is beta. Let us say this is beta. Okay. Now, this is alpha. Let us say at this point I need to see, so that my tangent position can be properly reflected. So, at this point if I draw the tangent, let us say let me draw the tangent here, okay, and let us say at this position I draw another tangent. Okay. So, this is nothing but, so this is tangent over beta. So, this will be B bar with beta in beta phase, and this will be G A bar in beta phase, and this is G A bar alpha phase, because this will be, this is on alpha phase, and this is G B bar alpha phase. Okay. This is alpha phase, yes, fine. So, if I try to find out, these are the two compositions, let us say. This is C1 and let us say this is, and this C1 and C2 are basically with respect to B. That means, those are actually mole fraction of B at those 2 points over alpha and beta G2 line. And remember, this is G2 beta, G2 alpha. Now, if I try to find out composition in between C1 and C2, so if I draw that particular composition, let us say this is C, and if I try to find out the difference of free energy, this to this free energy difference, or this free energy difference between the points of the tangent over alpha composition and the beta composition, that tangent over beta composition, that is cutting across the composition at C. So, this is C2 at C. So, this composition where that is cutting. So, that is basically the difference. In order to find out that difference, I can actually do it by shifting the equilibrium point over the tangent over alpha point and tangent over beta point. So, now for alpha, I can write this G2 at composition C, starting from C1, I can write this 1 minus C into G A bar alpha plus 1 plus C G B bar alpha. Similarly, for beta, I can write, and this is alpha, G2 beta C, starting from C2, I can write 1 minus C G A bar beta plus C G B bar beta. Okay. So, let us say this point is A and this point is B. So, this reflects at A point and this reflects at B point. Okay. Now, I can find out delta G at C between alpha and beta phase. So, I can write which one is lower. Lower is G2 beta C C2 minus G2 alpha C C1. So, it comes 1 minus C G A beta bar minus G A bar alpha plus C G bar beta minus G B bar alpha. Okay. So, that is the free energy difference between these 2 points A and B. In fact, if I zoom these particular sections, only these 2 if I try to consider. So, this is one line, this is G A G B bar alpha, this is G A bar alpha, this is G B bar beta, this is G A bar beta, and at C if I reflect this is, so this is the value we are trying to find out, this is the delta G. So, this delta G is reflected with this particular formula. Now, we see that there is a free energy difference and this free energy difference is negative. So, this is negative because if I see properly G, the tangent at C over the beta phase, this particular tangent. So, that means the point at B and A, B is at a lower free energy compared to A. Okay. So, that means there is a free energy lowering equal to delta G, this is less than 0. So, that means there should be diffusion or the transfer or the migration of components from one phase to another, because I see that these two values are different. Okay. Alpha G A alpha and G A beta as well as G B beta as well as G B alpha, those are different values and that is reflected by this difference. Okay. So, hence there would be migration. Now, let us understand the migration part. So, migration would be like this, since G A alpha is less than G A beta, hence A will migrate from beta phase to alpha phase. Since the escaping tendency of A from both the solutions are different and there is a net negative value when I am talking about G A alpha minus G A beta. So, that is a negative quantity. So, that means there should be a flow of A from beta phase to alpha phase. Now, if we go to the other side, G B beta less than G B alpha, hence B will migrate from alpha phase to beta phase. Okay. Now, this is interesting. So, if A moves from beta to alpha, so that means the composition of alpha will switch to the side which is lesser in B. So, this will be this side it will move, and on the other side, since B will move from alpha phase to beta phase. So, beta phase will be enriched with B. So, the composition will switch to this because of that migration of both the components from one phase to another. So, if it moves, that movement must happen over the G2 line, okay, for alpha as well as beta. So, if that movement happens, so that movement will gradually, so that movement will be slowly from this point to this point like this, and on the other side if I consider, so it will be this like that way over that G2 line alpha and beta for both the phases. The composition will be enriched in such a fashion that alpha will be enriched with A and beta will be enriched with B. So, now if that happens and if we start drawing the tangent over those switched point because of that migration, we see that this line gradually will actually, this particular tangent over alpha gradually would switch it will switch like this. it will switch like this, fine. And similarly, this beta point would also switch like this. So, it would be also fine. So, that means this line will move downwards and this line this tangent will move downward and this tangent will move upward. And there will be a situation that where the common tangent will go to a the tangent over both the alpha and beta free energy, that is G2 line, will pass through the same tangent. So, that will be same tangent. Okay. That switch will be such that finally they will be a common one between both the phases. Okay. So, now if I try to draw it here with the same concept, this is for G2 alpha and then another one is basically for G2 beta. So, now you see it would be finally the tangent movement would be such that finally both the tangents over alpha composition and beta compositions, those 2 points, 2 tangents will merge with one single tangent. So, that is what it would become common tangent. Okay. Since the composition started shifting this way and composition over the beta will be shifting like this, and the tangent will mutually switch because of this migration, and then both the tangents over alpha and beta points. So, this would be my C alpha and this will be my C beta. These two compositions, 2 tangents will be merging with each other. So, that becomes common tangent. And then I see this is interesting point. Here I see that G A bar alpha is equal to G A bar beta, and here I see G B bar alpha equal to G B bar beta. So, that means escaping tendency of A in both alpha and beta phase and escaping tendency of B in both alpha and beta phase all are equal. So, that means there will be no net movement of any component from one phase to another, because all the free energy difference, that is delta G, this delta G has ceased because it has come on a same platform. So, that is what the common tangent talks about equilibrium between 2 phases, and that time the escaping tendency of A and B in both alpha and beta phase are same. So, that is reflected with the chemical potential. Okay. So, now why we have started doing this? Just to understand why we need to construct common tangent to understand the chemical equilibrium between 2 phases. And here another interesting point is that equilibrium between alpha and beta phase is applicable only at two composition points. So, those two composition points are this one and this one. So, these two composition will be under equilibrium, and any other point over beta or alpha free energy line, that is G2 alpha or G2 beta, you will see that there will be always some difference between the chemical potential of A in alpha and beta and B in alpha and beta. So, there should be a net movement in order to go to an equilibrium condition. So, for example, if I take point here and if I take a point here for beta, so if I see again, I draw a tangent. So, this tangent would be here and here the tangent would be at this point if I try to draw it. So, this will pass through this. Okay. I see that again there is a net difference between the chemical potentials of A and B in both the phases. So, the system, any system, and these are all at particular temperature pressure. Remember, temperature and pressure, that means are constant, are fixed. So, that means we are under thermal and mechanical equilibrium. The only thing that is left the system to achieve is basically chemical equilibrium. That is applicable, and if there are difference between the chemical potentials of A and B in both the phases, there will be always a kind of drive of the system to reach equilibrium, because every system wants to reach stability. So, that is what finally it will come to that common tangent and system would reach equilibrium. So, this common tangent is applicable for that two composition C alpha and C beta. So, this is applicable at two specific compositions. Okay. So, these are C alpha and C beta. Remember, these are with respect to B. Okay. So, with this common tangent concept, now we will go and try to see how the phase diagram evolves if we take solid and liquid phases in A and B system, A and B, that is a binary system, and how those all those particular at particular temperature and with the change in temperature at a constant pressure, which is 1 atmosphere, how those equilibrium points shifts or switches from one particular composition to another compositions. Okay. So, that we will see in the next class, and that will give us the phase diagram, which is called isomorphous phase diagram. So, let me stop here. We will continue our discussion. Now, we will start building up phase diagrams. Thank you very much.